And our next speaker will be Lucas, who is going to tell us a bit about disornamentation, or the right approach to ornamentation, is it? Okay.
I'm going to talk about disornamentation, or whether ornamentation, or as it should have been. So this is a joint work with DGRB that we did at INERIA in Paris. So when one programs, data structures play a important role for code performance or for code readability. That is why data structures of existing programs may need to be verified. In that case, the existing piece of code that use this data structure might be modified accordingly, and doing so by hand is tedious, maybe incomplete, and errorful. So in the context of the ML family of programming languages, ornamentation is a class of transformation that semi-automatically adapts pieces of code to changes in data structures. It's a form of refactoring, even if ornamentation is more complex than the transformation that are usually put in the category of refactoring. So for instance, if we take a type X, which can be used to represent a small language with application, abstraction, posters, we may want to add location information so that we can handle errors and do proper error reporting. Data type modification can be written as a relation between values of type X and values of type X plus. For instance, values which start with super app are related to values which start with super app prime, and the arguments of these constructors are also related. So here we have the same variable on the left and on the right, but actually there are two different variables. There is a no-range view and a print view, which are related with the same add operation. So this is a locally defined relation. And then there is a wildcard here for location, meaning that we can put any location. So it's similar for abstractions, and the constants are just related to. So this is an ornament, and ornamentation is a mechanism that semi-automatically adapts functions operating on type X to functions operating on type Y. More generally, ornamentation is a process that can be used to add pieces of data to the data structures, that can be used to reorganize constructors, rename constructors, or more surprisingly, remove constructors. And disornamentation is the reverse transformation. It can be used to remove pieces of data or reorganize constructors, rename them, or add. So ornamentation was already studied prior to this talk. So today I'm going to present how disornamentation can also be done semi-automatically. However, I'm going to show how the ornamentation framework can be extended so that it supports more than just ornaments, but also disornaments or relations that are a mix of both. Ornaments are quite a new topic because they were first brought up by Conor McBride with Kerry Hexagon in 2012. It was also studied by Tim Pro and Jeremy Gibbons. And this work is based on work by Thomas Williams and DGRB, which adapted the idea of ornaments to them. Once we have both ornamentation and disornamentation, they can be used to synchronize between two views of the same algorithm. For instance, we have a view which uses type X, which has a code that is simpler, but which has no error handling. And then we have a second view, which uses type X-block, but where the code is bigger. There is a proper error handling, but the code is less readable. So ornamentation and disornamentation can be used to switch between those two worlds. And as we are going to see at the end of this video, ornamentation may need patches to properly do this function. So both disornamentation and disornamentation were implemented in the prototype, which was originally developed for ornamentation. I'm going to make here is another example of ornamentation. So we have a type NAT for piano number, the list, and we can write a relation between those two types. Indeed, we can relate the 0 to the list, and then the successor of x to the cons of any element, and x, where x is also a relation between NAT and the same relation. So once we have defined this relation, we can use it to lift a function that operates in type NAT. So for instance, if we take the addition function, which performs the addition to two piano numbers, we can lift this function using this instruction, lifting, and then we specify that we ornament both the two arguments of this function and the return type, and we get this function, which has a pole here because we have not specified what must be put in the pole. So this can be done by specifying the patch in the lifting declaration. So we use the whole number, H3, and then we put the patch function, and it is reduced inside the function. So we get the concatenation function between two lists. So this was a non-ornamentation example. So now an example which mixes both ornamentation and disornamentation. So which presents the code synchronization feature. So here we change to a mode. So we have two views, which can be used to generate the other one. So the prototype generates the lifting that we ask, but it also generates the code that is needed to go back to the previous view. So we can switch between those two views, and the code is automatically updated on both sides. So here we are going to use. So now we take the lines function, which takes a list and returns the piano number, which is its length, and we are going to ornament it and disornament it at the same time. So we disornament the argument of this function, so it goes from list to piano numbers, and then we ornament the return type of this function, and we get a list inside of piano numbers. So the goal is to get a function that computes the list of the numbers from 1 to n. So with this declaration, we get this function which has a pole, and we could do like in the previous example and specify the patch manually, but we can also take advantage of the code synchronization feature and just edit here the pole, and a patch is automatically generated to fill it here. Then we can go back to the overview, and we see that the patch doesn't have numbers, so it means that it can fill any pole. And so, for instance, if we instead of use 0 for the base return type, we can use successor of 0. And then here we should have a pole which appears, but it is automatically filled by which. And now if we switch again back to the overview, we can change the value here, for instance, 0. And then two different patches are generated for the first pole here and the second one here. And we can even remove completely the points in this branch. And we get back the original length function on the left.
In the state with the two patches, the patch were specified by matching the value of n, not by number.
Yes, so this is another contribution of this work. It's that we don't only use the number, which are not robust enough, and we use term patterns to select poles, and so we are going to see this at the end. The framework to perform the transformation is strongly inspired from the one devised for ornamentation in ML. So it's a two-step framework. First, the initial term D is elaborated into a generic term, which is written in meta-ML, which is a language like ML but with a meta construction. This is done independently on any relation of the return type. And then the generic term is specialized with specific relations to ML term, which operates on the direct type. So this transformation is proven correct using a logical relation, which expresses the fact that relation in the target term can be tracked into reductions in the initial term. So the elaboration step was adapted from the one device for ornamentation, and the specialization step was also adapted, and it was extended with the new step because users code elimination. And the logical relation was also extended to support both ornamentation and disornamentation, and we had to check that the proof was different. So first, the elaboration step. The generic term uses skeleton types. A skeleton type is defined for every data type. It's a data type that has the same constructor, but where the type of the arguments are abstract. So here, for the skeleton list, we get new constructor. We get the same constructors, but with arguments of different types. Here we have alpha and beta, which are also arguments of this skull. So the point of these skeleton types is that it is more flexible, so it can be used to represent values that are intermediate between list and null, for instance. So if we take the length function that we saw in the demo, we get this generic term, which is obtained by putting conversion functions in pattern match expression and before constructors with values. It is parameterized by two records, well1 and well2, which are used to encode relation. So they contain four functions. The from scale and to scale functions are used to convert from the target type to the skeleton type. And then there are also two type functions that describe the type of extra information that are needed to convert from and to the skeleton. So here, these extra information are sharp3, sharp5, and sharp7, and these are the holes that may still be at the end of the transformation and that the user need to specify. So before we can instantiate this generic term, we'll see how relations are encoded in this record. So for instance, if we take the relation lattice that we saw in the demo, it is defined with a set of clauses. They are used in the to-scale and from-scale functions, and also in the from-scale, in delta-to-scale and from-scale functions. Here we can see that the delta-to-scale is constant to unit. It's the case because there is no need for extra information to go from a list to a skeleton of NAT, because there is nothing new. But this is not the case for the reverse relation, list, where we go from NAT to a skeleton of lists. So here we need to put to have extra information. That is the element of. That is all of the difference with ornamentation, because for ornamentation we could just we did not have this solution, and for disornamentation we need them as we can be more information in the initial type and then the type. So once we have this encoding, we can instantiate the generic type and then reduce it and simplify it. So we remove meta-ML constructions, so we get an ML term. And then we need a new subset, which is the useless code elimination subset. Indeed, for an ornamentation, we only added pieces of information to the data type, and so no code needs to be removed. But for disornamentation, the code used to, for disornamentation, we remove pieces of information from the data type. So the code used to compute this removed piece of information becomes useless. For instance, if you take the map function, there is a prime value that is computed, and when we disornament this from list to NAT, then a prime is still here, but there is not the argument of function anymore because it was the element of the list, and worse, a prime is not used anymore, so this is not needed, and it should be used, so that the correct one, and so it's better if it's removed. And more generally, we remove every piece of code that becomes useless after its function. So, as we saw in the demo, the synchronization extensively relies on the batch language. The batch language that was used for ornamentation relied on holds with number. And this has several advantages. For it's not reduced to changes, so for instance, if we code changes, then the numbers may also change. It did not allow easy patch vectorization, and patches could not be extended to new and similar holds. So this was the patch that was used for the function. So to the point that was already noticed for with ornamentation, but not solved, and for point synchronization, this is worse because we want to be able to change the code and to have robust patches. So in our new patch language, a patch is composed of a pattern which is used to select holds. It is a term with meta variables and a Unicode denoted sharp with brackets. And inside these brackets, there is a term which is the patch content. And here, the term pattern is in orange and is used to select the fold into that prime. So there is correspondence to the first. And then the content of the patch is the blue part. So we replace sharp 3 with only the content of this patch. So the patch. The content of the patch may use capture variables that are written in the pattern written by the user, or in another part of the patch, the top level pattern that is implicitly decided by the prototype and which is used here to bind the top level argument function. And then the patches are also composed of pattern variables which is used to match the patch inside the term. So it means that patches are not necessarily double. So another thing that the synchronization needed was patch generation, and I'm going to explain why. So I'm going to explain why we need to code the patch generation when there is addition in this group part. So, but there is a similar thing for our side. So let's suppose we have a function evaluate in the explore world, we disornament it to an eval function, and then we edit this eval function in this world, where a function operates in x, to a function eval prime. And we want to be able to go back to the x block world where a function operates on eval prime. So the question is, how do we go from eval prime to eval prime? And the idea is that we are going to use the same transformation as one that is used to go from eval to eval lab. So as we disornament in one way, we are going to ornament in another way. But unfortunately, ornamentation needs patches that this is a code that may be removed by disornamentation. And we need to generate more. So to do this, we first ornament eval without patches, and we get function eval sharp, which is incomplete. And then we can compare this function with normalization of eval lab, and we can deduce the content of the patches, and then the term patterns are used to say the holes. So we get some patches P, and they can be used to go from eval to eval lab, or below the normalization of eval, and we can try to use them as well to go from eval prime to another function eval lab. So as a conclusion, we devised a new framework that uses both theory and implementation of ornamentation. This new framework is more general and can be used by both disornamentation and ornamentation. Ornamentation and disornamentation make it possible to do code synchronization, and to do this we need a new patch language as well as patch generation. There is local implementation that is being done for ornamentation, because currently this prototype only works in a subset of ML, and we can probably add the disornamentation to the future prototype.
All right, are there any questions? We've got some time. Okay, well.
So I have a question on the eval log slide, so 2 slides ago. So here there is an assumption that the normalization of eval log will give you code that is similar in shape to the result of ornamenting eval, so that you can actually find the patches. Is it something that is always true, that you have proven it or you prove it, or is it most of the time true?
So we have not proven it. And it's not always true, because if disornamentation is true destructive, then we can remove too much code, and then we cannot go back to this part. But I think there are constraints on the relation that is used between x and x block, which makes it possible to prove that we get the normalization, if we have the patches. And this is something that we would like to do to prove more properties about the disornamentation that is then followed by ornamentation.
Okay, I think let's thank Lucas again. And the final talk in this session is on generic programming with combinators and objects, and it's by